This is the EdExcel A-Level Further Maths Paper 3, covering the Further Pure 1 FP1 module, and this is from the 2022 series. Question number 1. An ellipse has equation x squared over 16 plus y squared over 4 equals 1 and eccentricity E1. A hyperbola has equation x squared over a squared subtract y squared over b squared equals 1 and eccentricity E2. Given that E1 multiplied by E2 is equal to 1, for part A we have to show that a squared is equal to 3b squared. Now the eccentricity of an ellipse and a hyperbola are shown here. And what we can do is use the standard form of an ellipse and a hyperbola to help us find out what E is. So for part A of the question, we have x squared over 16 plus y squared over 4 equals 1, and therefore with eccentricity we have for an ellipse b1 squared equals a1 squared multiplied by 1 subtract e1 squared. So b1, that's equal to 4, and this is equal to a1, which is 16, multiplied by 1 subtract e1 squared. And from this we can therefore conclude that E1 is equal to 3/4. So E1 squared is equal to 3/4. Now if we consider the hyperbola, where we have x squared over a squared subtract y squared over b squared equals 1, then what we have is, using eccentricity, b squared, which is equal to a squared multiplied by e2 squared subtract 1. Now if we know that e1 multiplied by e2 is equal to 1, what we can conclude from here then is e2 is equal to 1 over e1, and if I square both sides, e2 then will equal 1 over e1 squared. So what we can do is substitute in this and this into this, and so we have b squared equals a squared multiplied by e2 squared. Now e2 squared, we've just said that's the same as 1 over e1 squared, and then we subtract 1. And knowing what E1 squared is, that's 3/4, we have B squared equals A squared multiplied by 1 over E1 squared, so that's 1 over 3/4, which is 4/3. So we have 4/3 subtract 1, and therefore, recognizing that 4/3 subtract 1 is equal to 1/3, and then multiplying through by 3, we can conclude A squared is equal to 3B squared. Given also that the coordinates of the foci of the ellipse are the same as the coordinates of the foci of the hyperbola, we have to determine the equation of the hyperbola. So what we need to do here is find out the value of A and find out the value of B. And we also need to find out the value of E2. Well, first of all, if we know that E1 squared is equal to 3/4, what we can see from that then is E1 is equal to the square root of 3/4, which is equal to root 3 over 2. And what we know for on an ellipse and a hyperbola, the foci is given by plus minus AE 0. And we have the same foci for both the ellipse and the hyperbola. So, for the foci, the coordinates will be given by plus minus AE 0. Now, if E1 is equal to root 3 over 2, that means E2 will equal, well, if we know that E1 multiplied by E2 is equal to 1, we can find out what E2 is. That will equal the reciprocal of root 3 over 2, which is 2 over root 3. So if we consider the x-coordinate of the foci of the ellipse, the x-coordinate, we'll call it xf, that's equal to AE. Now the value of A over here is the square root of 16 multiplied by the value of E, which is root 3 over 2. So the x-coordinate of the ellipse then is equal to 2 root 3. And if we consider the hyperbola, then the x-coordinate of the foci will equal A multiplied by 2 over root 3, which is equal to 2 root 3 A over 3. And because the foci are the same for both the ellipse and the hyperbola, they would have the same coordinates, which means that the 2 root 3 a over 3 will equal 2 root 3, which means a is equal to 3. And if a is equal to 3, we can use our result here to help us find out what b squared is. Well, if a is equal to 3, that means a squared is equal to 9, which means we have a squared, 9, equals 3b squared, which means b squared is equal to 3. And therefore, the hyperbola would have equation x squared over 9 subtract y squared over 3 equals 1. Question number 2. During 2029, the number of hours of daylight per day in London, h, is modelled by the equation h equals 0.3 sine of x upon 60, subtract 4 multiplied by the cosine of x upon 60 plus 11.5, where x is in between 0 and 365. X is the number of days after the 1st of January 2029, and the angle is in radians. For part A, we have to show that according to the model, the number of hours of daylight in London on the 31st of January 2029 will be 8.13 to 3 significant figures. Well, what we are doing here is considering what happens when x is equal to 30, and that's because we are going from the 1st of January to the 31st of January, so we have 30 days. And if we substitute in x equals 30, as we see here, with this we can find out what h is. So, substituting this in, we've got 0.3 multiplied by the sine of 30 over 60, subtract 4 times by the cosine of 30 upon 60, plus 11.5, and it turns out h is equal to 8.1334, etc. So to 3 significant figures, h is equal to 8.13, and that's given to 3 significant figures, and the units are hours. For part B of the question, we have to use the substitution t equals tan of x upon 120 to show that h can be written as h equals at squared plus bt plus c over 1 plus t squared, where a, b and c are constants to be determined. Well, for part B, if t is equal to the tan of x upon 120, then sine of x upon 60 is 2t over 1 plus t squared, cos of x upon 60 is 1 minus t squared over 1 plus t squared, and tan of x upon 60 is 2t over 1 minus t squared. So, if we substitute this into what h is equal to 0.3 multiplied by, well, here we've got 2t over 1 minus t squared, subtract 4 multiplied by 1 minus t squared over 1 plus t squared, and then we add on 11.5. So let's work all of this out. Rather, here we've got a plus. So h is equal to, well, here I've got 0.3 times by 2t, subtract 4 multiplied by 1 subtract t squared, and then if I want my denominator to be 1 plus t squared, then I would add on 1.5 multiplied by 1 plus t squared, and then on the bottom we would have 1 plus t squared. So let's simplify all of this. Well, if we were to simplify, we can therefore conclude h is equal to, well, just in terms of the t squareds, I've got 11.5 plus 4 of them, so that's 15.5 t squared. Then we add on 0.6 multiplied by t, and then we've got minus 4 plus 11.5, so we add on 7.5, and then we will divide this entire result by 1 plus t squared, and that's exactly what we wanted to show. The value of a is equal to 15.5, the value of b is equal to 0.6, and the value of c is equal to 7.5. Here are our values. For part C of the question, hence determine according to the model the date of the first day of 2029 when there will be at least 12 hours of daylight in London. Well, when h is equal to 12, we set this result equal to 12 as we see here. So we have 15.5 t squared plus 0.6 t plus 7.5 equals 12 multiplied by 1 plus t squared. So if I simplify all this, well, I've got 15.5 t squared subtract 12 t squared, so that's going to give 3.5 t squared. And then I've got the 0.6 t. And then I've got 7.5 subtract 12, so that's going to give minus 4.5. And all of this is equal to 0. So now I need to find out what t is. So if I attempt to solve for t, we can just use our calculator. If we go to the equation solver, we've got a polynomial of degree 2, type in the coefficients. And it turns out we get t equals 1.1 0.05, etc. Now let's store this into A. And the other value we get is minus 1.22, etc. Let's store this into B. So we would clearly reject this value here, and knowing that t is equal to the tangent of x over 120, we therefore have the tangent of x over 120 equaling 1.05, etc. So if we take this value of 1.05, etc., and then take the inverse tangent of it, and then multiply this by 120, we get x equals 97.2, etc. And knowing that x is equal to 97.2, etc., what we need to do is add on 97.2, etc. days onto the 1st of January. So we have the 1st of January plus the 97.2, etc. days. So what we end up with is the 9th of April 2029. Question number 3. With respect to a fixed origin O, the points A and B have coordinates 2, 2, minus 1 and 4, 2, P, 1, respectively, where P is a constant. For each of the following, we have to determine the possible values of P for which, for part A, OB makes an angle of 45 degrees with the positive x-axis. So for part A, before we do anything else, we need to find the magnitude of the vector OB. So the magnitude of the vector OB, well, we have 4 squared plus 2p squared plus 1 squared, then this is square rooted. 16 plus 1 is 17, and then we add on 4p squared. So what we end up with is 17 plus 4p squared square rooted. Now that we know what the magnitude of OB is, to find out the angle, well, we know the angle, and if we use the direction cosine, we've got the cosine of 5 degrees equals, well, the x component here is 4. So we have 4 divided by 17 plus 4p squared square rooted And therefore, knowing that the cosine of 45 degrees is root 2 over 2, we have root 2 over 2 equals 4 over 17 plus 4p squared square rooted, as we see here. And then if we square both sides to find out what p is, we have 1/2 equals 16 over 17 plus 4p squared. So 17 plus 4p squared is equal to 32, which means if I attempt to solve for p is equal to plus minus root 15 over 2. Then for part B, we have to find the possible values of p for which the vector OA crossed with OB is parallel to 4 minus p 2. So for part B, the vector OA cross with OB, that's equal to, well, what we have here is the vector OA, so that's 2i plus 2j minus k cross with 4i plus 2p j plus k. So if we work this out, well, we've got I, j and k, and if we enter in this vector, we've got 2, 2, minus 1, and if I enter in this vector, we've got 4, 2p and 1. So if we work this out, well, along the I component, we have 2 subtract negative 2p, so that will be 2 plus 2p I. And in the j component, well, we've got a minus because we've got the sign convention, plus minus plus, that we need to consider. So with the j, we've got 2 times by 1 subtract 4 times minus 1, so we've got 2 plus 4, which is 6. Don't forget the minus, so we subtract 6j, and then for the k, we've got 4p subtract 8. So we add on 4p subtract 8k. And if we were to write this as a column vector, then we have 2 plus 2p minus 6, 4p minus 8. Here is the vector OA crossed with OB, and what we need to do is find the value of p such that OA crossed with OB is parallel to 4 minus p 2. And so if that's the case, what we have is 2 plus 2p minus 6, 4p minus 8 equaling 4 lambda minus p lambda 2 lambda. Now, if we take a look at the components, well, we have 2 plus 2p equals 4 lambda, minus 6 equals minus p times by lambda, 4p minus 8 equals 2 lambda. Now we need to find the value of p. Now if I call this equation 1, this equation 2, and this equation 3, what I can do is multiply equation 3 by 2, leaving me with well, 4p times by 2 is 8p, minus 8 times by 2 is minus 16, 2 lambda times by 2 is equal to 4 lambda. Now if I call this equation 4, I can set equation 1 equal to equation 4, leaving me with 2 plus 2p equals 8p minus 16, which means if I solve for p is equal to 3. This is our only solution. For part C, we have to find the value of p for which the area of the triangle OAB is 3 root 2. So for part C of the question, we've got 1/2 multiplied by the magnitude of OA cross with OB equals 3 root 2. And if I multiply by 2, we have the magnitude of OA cross with OB equals 6 root 2. Now, happily for us, we've already worked out OA cross with OB. We worked that out over here. So, we've got the magnitude of OA cross OB, so we've got the magnitude of 2 plus 2p minus 6, 4p minus 8, equaling 6 root 2. Now, let's find the magnitude of this vector. Well, what we would have is 2 plus 2p squared plus minus 6 squared plus 4p minus 8 squared square rooted. This is equal to 6 times by the square root of 2. And if I square both sides and then also expand the brackets, what we have is 4 plus 8p plus 4p squared plus 36 plus 16p squared minus 64p minus 64 equals 72. Take everything over to one side and simplify. We have 20p squared minus 56p plus 32 equals 0. Now let's attempt to solve for p. We have 20p squared minus 56p plus 32 equals 0. So we can either see p is equal to 2 or p is equal to 4/5. Question number 4. The velocity v meters per second of a raindrop t seconds after it falls from a cloud is modelled by the differential equation dv over dt equals minus 0.1 v squared plus 10, where t is greater or equal to 0. Initially, the raindrop is at rest. For part A, we have to use 2 iterations of the approximation formula shown here to estimate the velocity of the raindrop 1 second after it falls from the cloud. So for part A, first of all, we are using 2 iterations. We are going from 0 seconds to 1 second with 2 iterations. So h is equal to 0.5. Now we've got this iterative formula. dy over dxn is approximately yn plus 1 subtract yn over h. If we rearrange this, we can see that yn plus 1 is approximately yn plus h multiplied by dy over dxn. So, first of all, we know that t0 is 0 and it starts from rest, so v0 is also equal to 0. And with this we can find out what dv over dt naught is. And we can do this by using the differential equation. So using the differential equation, we've got minus 0.1 v0 squared plus 10. So we've got minus 0.1 multiplied by 0 squared plus 10, which is equal to 10. And now what we can do is find out what v1 is using the iterative formula. So to find out what v1 is, well, t1, that's equal to 0.5, and therefore v1 is equal to, well, that's equal to v0 plus h multiplied by dv over dt naught. So we've got v0, which is 0, plus h, which is 0.5, multiplied by dv over dt naught, which is 10. So I've got a half of 10, which is 5. And then what we need to do is find out what v2 is. Well, for us to find out what V2 is, what we need to find out first is dV over dt 1 is. So we've got minus 0.1 V1 squared plus 10. So I've got minus 0.1 multiplied by V1, so that's 5, squared plus 10. So I've got altogether 7.5. And now what we can do is find out what V2 is. Well, to find out what V2 is, that is when T2 is equal to 1. And knowing that T2 equals 1, V1, rather V2, is equal to V1 plus H multiplied by dV over dt 1. So if we find out what V2 is, we have V1, which is 5, plus H, which is 0.5, multiplied by 7.5, and if I work out what this is, I get 8.75. So V2 is approximately equal to 8.75 meters per second. Next, given that the initial acceleration of the raindrop is found to be smaller than is suggested by the current model, we have to refine the model by changing the value of one constant. Well, dV over dt would represent the acceleration. Now, we are told that the initial acceleration is smaller, and we can get a smaller acceleration by reducing this constant of plus 10. And therefore, for part B of the question, our new model, we've got dV over dt equals minus 0.1 v squared plus some constant a, where a is in between 0 and 10. Question number 5. The rectangular hyperbola h has equation xy equals 36. For part A, we have to use calculus to show that the equation of the tangent to h at the point P with coordinates 6t and 6 over t is yt squared plus x equals 12t. First of all, for part A, we are given that xy is equal to 36, and if I differentiate implicitly, we will end up with x multiplied by dy over dx plus y equals 0. And therefore, we can see that dy over dx is equal to minus y over x. Now, if I consider this point P with coordinates 6t and 6 over t, then what we can do with this is find out what dy over dx is at this point. So dy over dx will equal at this point, well, we've got y, which is 6 over t, and we've got x, which is 6t. So dy over dx is equal to minus 6 over t divided by 6t. And it turns out what we end up with is minus 1 over t squared. And now what we can do is find the equation of the tangent at this point. We've got y minus y1 equals gradient minus 1 over t squared multiplied by x minus x1, which is 6t. And if I simplify all this, we end up with y t squared plus x equals 12t. Now we'll call this equation 1. For part B of the question, the point Q with coordinates 12t and 3 over t also lies on H. We have to find the equation of the tangent to H at the point Q. Well, we've got the same idea over here. Instead of using 6t and 6 over t, we use the point 12t and 3 over t. So we end up with dy over dx equals, well, I would have minus 3 over t over 12t which is equal to minus 1 over 4t squared. So, for the equation of the tangent, we would have y minus 3 over t equals 1 minus 1 over 4t squared multiplied by x minus 12t. And therefore, rearranging, we can see we have 4y t squared plus x equals 24t. We'll call this equation 2. So here is the equation of the tangent at the point P, and here is the equation of the tangent at the point Q. Next, the tangent at P and the tangent at Q meet at the point R. We have to show that as t varies, the locus of R is also a rectangular hyperbola. Now, what we have here is our hyperbola. We've got the point P shown here. We've got the point Q shown here. We've got the tangent at P shown here, and the tangent at Q shown here. And the tangents meet at this common point. Let's call this common point X, as we see here. And what we are saying here is, as this point X moves around, what's formed is another hyperbola. So as A varies, of course X varies with it, and the locus of points will form a hyperbola, and that's what we see here. So you can see the point x follows that hyperbola path, which is shown dashed. If we zoom in, you can see it follows the path of a hyperbola, and we need to find the equation of this hyperbola. So what we'll do is we'll find out the point of intersection in terms of t, and what we can do is work out equation 2 subtract equation 1. So 4yt squared subtract yt squared, that is 3y t squared. X subtract x is 0, and then we've got 24t subtract 12t, which is 12t. And therefore, if we solve for y is equal to 4 over t. So now that we know what y is, we can find out what x is. Now if we go back to the equation, we've got xy equals 36, and therefore x is equal to 36 over y. So now let's use this to find out what x is. So x will equal 36 over 4 over t. And therefore, what we end up with here is 8t. Now, a hyperbola is of the form xy equals c squared. That's a rectangular hyperbola. So, we have x squared, rather we have xy equals c squared. This is for a rectangular hyperbola. So we've got x, which is 8t, multiplied by y, which is 4 over t. And what this is equal to is 32. So c squared is equal to 32, which means the equation, we've got xy equals 32 as the equation of our rectangular hyperbola. Question number 6. The points P, Q and R have position vectors 1, minus 2, 4, 3, 1, minus 5, 2, 0, 3 respectively. We have to determine a vector equation of the plane that passes through the points P, Q and R, giving your answer in the form R equals A plus lambda B plus mu C, where lambda and mu are scalar parameters. Now first of all, we need to find out what the vectors A, B and C are. So the vector A can be any of these points. I'm going to choose the point P. For B, well, B, that direction vector can equal PQ. And if I work out PQ, well, from 1 to 3, I go 2 in the X. From minus 2 to 1, I go 3 in the Y. And from 4 to minus 5, I go minus 9 in the Z. So the vector B is shown here. And for the vector C, that's equal to PR. So we are going from P to R. So from 1 to 2, we go 1. From minus 2 to 0, we go 2. And from 4 to 3, we go minus 1. So here is the vector C, 1, 2, minus 1. And now what we can do is write down our equation of the vector. We've got R equals 1 minus 2, 4, plus lambda multiplied by 2, 3 minus 9 plus mu multiplied by 1, 2 minus 1. For part B of the question, we have to determine the coordinates of the point of intersection of the plane with the x-axis. Well, for part B, the plane intersects the x-axis when y equals 0 and z equals 0. This is where the plane intersects the x-axis. So, if that's the case, then what we have is the y component equaling 0 and the z component equaling 0. So I've got minus 2 plus 3 lambda plus 2 mu. And if I set this equal to 0, we can rearrange to say that 3 lambda plus 2 mu equals 2. And what we also have is, well, let's just say here we've got the condition for z equals 0. Then what we have is 4 minus 9 lambda minus mu equals 0. So 9 lambda plus mu equals 4. And what we can do is solve these two equations simultaneously. And if I solve those two equations simultaneously, well, I've got 3, 2, 2, 9, 1, 4. So I've got 2/5 and 2/5. So both lambda and mu are equal to 2/5. So, if that's the case, what we can do is find out what the x coordinate is by substituting 2/5 into the x component. So, x is equal to 1 plus 2/5 multiplied by 2 plus 2/5 multiplied by 1, and this is equal to 11 over 5. So I've got 11 over 5, 0, 0, where the plane intersects the x-axis. Question number 7. Figure 1 shows a sketch of the curve with equation y equals the mod of x squared minus a and a sketch of the straight line with equation y equals mx plus c, where m and c are positive constants. The equation mod of x squared minus a equals mx plus c has exactly 3 roots as we see in figure 1. It's got a root here, here, and here. For part A, we have to show that m squared minus 4c plus 32 equals 0. So, for part A, we've got x squared minus 8 modded equals mx plus c. So we've got plus minus x squared minus 8 equals mx plus c. And what we need to do here is consider the negative solution only. That's to say we've got 8 minus x squared equals mx plus c. And the reason for this is because of the shape of the graph. So let's write this down. We've got the negative shape of the graph, which is why we've got this negative only being considered. So we have x squared plus mx plus c minus 8 equals 0, and because we see that this line touches the curve exactly once, at that point we need to set the discriminant equal to 0. So we've got m squared minus 4 times by a times by c equals 0, leaving us with m squared minus 4c plus 32 equals 0. And that's exactly what we wanted to show. For part B, given that c is equal to 3m, we have to determine the value of m and the value of c. So what we need to do is replace the c with 3m. So for part B, when c equals 3m, we have m squared minus 12m plus 32 equals 0, factorize. We've got m minus 4 times by m minus 8 equals 0, which means m is either equal to 4 or 8. And if I attempt to find out what c is in this case, c is either equal to, well, I've got 3 times by 4, which is 12, and I've got 3 times by 8, which is 24. Now, if I have the m equals 8 and the c equals 24 into this equation, let's see what happens. So let's just write this down. If I have m equals 8 and c equals 24, I have 8 minus x squared equals 8x plus 24. And that is, with that positive equation, leaving me with x squared plus 8x plus 16 equals 0. So x plus 4 all squared equals 0, which means x is minus 4. And from this I can find out what y is. Y equals 8 times by minus 4 plus 24, which is minus 8. So this point of minus 4 minus 8, this is below the x-axis. And I want my straight line to intersect this curve on the above the x-axis. So that means that m equals 4 and c equals 12 is the only solution. Now for part C, hence solve the mod of x squared minus 8 being greater or equal to mx plus c. Now, in other words, what we need to do is find out the 3 points of intersection. Our critical values, in other words. So, what we are looking to solve is x squared minus 8 equals mx plus c. So here we've got 4x plus 12. So I've got x squared minus 8 equals plus minus 4x plus 12. So if I deal with the positive, x squared minus 8 equals 4x plus 12. X squared minus 4x minus 20 equals 0. Let's find out what x is. What we end up with is x equals 2 plus 2 root 2, and we also would have the minus of this as well. Now, if we think about it, we don't need to consider the negative, because if I somehow extend this curve like this, we have only considered the positive version over here. We don't need to consider a negative line which would cross elsewhere. So it's sufficient for us to just use this. And now what we can do is also find out where the curve intersects the line between this point and this point, and that's achieved by setting the minus solution, where I've got x squared minus 8 equals minus 4x minus 12. So I've got x squared plus 4x plus 4 equals 0, which means x equals the value of minus 2 only. So where is the modded graph greater than the straight line? Well, it's greater than the straight line between values less than or equal to this point, or this point here, and it equals over here. So here I've got that point 2. Here I've got 2 minus root 2 minus rather here we've got a 6 instead. So here I've got minus 2 root 6, and over here I would have the 2 plus 2 root 6. So therefore, for my solutions of this inequality, I've got x being less than or equal to 2 minus 2 root 6, x being greater or equal to 2 plus 2 root 6, and x equaling minus 2. For question 8, for the part A of the first part, we have to use differentiation to determine the Taylor series expansion of the natural log of x in ascending powers of x minus 1 up to and including the term in x minus 1 squared. So what we need to do here is, well, given that f of x is equal to the natural log of x, from this we can find out what f of 1 is equal to. That's equal to the natural log of 1, which is just 1. So natural log of 1 is 0. What we can now do is find out what f dash of x is. That's equal to 1 over x. So f dash of 1 is equal to 1 over 1, which is 1. F double dash of x, we've got minus 1 over x squared, and so f double dash of 1 is equal to minus 1 over 1 squared, which is minus 1. So what we can now do is use the Taylor series expansion, and if we were to use the Taylor series expansion, f of x is equal to f of 1 plus x minus 1 times by f dash of 1 plus x minus 1 over 2 factorial times by f double dash of 1 plus higher order terms. So if we find the series expansion of the natural log of x about x equals 1, the natural log of x then is equal to f of 1, which is 0, plus x minus 1 times by f dash of 1, which is 1, plus x minus 1 over 2 factorial times by f double dash of 1, which is minus 1. So I've got the natural log of x equals x minus 1 minus 1/2 times by x minus 1 squared plus higher order terms. And now we have to prove that the limit as x tends towards 1 of the natural log of x over x minus 1 is equal to 1. Well, as x tends towards 1, we see that as x tends towards 1, we have the natural log of 1 over 1 minus 1. So we've got something of the form 0 over 0. And what we have something here is an indeterminate form, so we have to use our Taylor series expansion. And if we were to use the Taylor series expansion, we've got the limit as x tends towards 1 of the natural log of x over x minus 1. That's equal to the limit as x tends towards 1. Now here we need to use our result which we found previously, so we've got x minus 1 minus 1/2 times by x minus 1 squared plus higher order terms, and then on the bottom I've got x minus 1. So I've got the limit as x tends towards 1 of 1 minus x minus 1 over 2 so if I work this out, what we have then is the value of 1, and that's exactly what I wanted to show. Next we have to use L'Hopital's rule to determine the limit as x tends towards 0 of 1 over x plus 3 times by tan of 6x times by the cosec of 2x. Well, this result here is the same as the limit as x tends towards 0 of sine x, sine of 2x over x plus 3 times by tan of 6x. 1 over cosec 2x is just sine x. Now if I take the limit as x tends towards 0, this is of the form 0 over 0, and therefore we have to use L'Hopital's rule. And if I were to use L'Hopital's rule, what I need to do is differentiate both the top and the bottom. Well, if I differentiate the bottom, well, first of all, I've got the limit as x tends towards 0, and if I differentiate the bottom using the product rule, what we end up with, well, I've got 1 times by tan of 6x, which is just tan of 6x, and then I've got the differential of tan of 6x, which is 6 sec squared of 6x multiplied by x plus 3, so that is 6 times by x plus 3 times by sec squared of 6x. And that's what I have on the bottom, and on the top, differentiating sine 2x, we end up with 2 cos 2x. So now I need to find out what this is. So, as x tends towards 0, I've got 2 times by the cosine of 0, which is just 2. And on the bottom, I've got 0 plus, now here I've got 6 times by 3, which is 18, times by 1. So on the bottom I've got 18. So the limit is equal to 1/9. Question number 9. A particle P moves along a straight line at time t minutes. The displacement x meters of P from a fixed point O on the line is modelled by the differential equation t squared multiplied by d squared x over dt squared minus 2t times dx over dt plus 2x plus 16t squared x equals 4t cubed sine 2t. And we have to show that the transformation x equals ty transforms this equation to the differential equation d squared y over dt squared plus 16y equals 4 sine 2t. So for part A, what we have is x equals ty, and if I differentiate this with respect to t, well, I have dx over dt, and then differentiating ty implicitly using the product rule, we end up with y plus t dy over dt. And if I differentiate this once again, d squared x over dt squared is equal to, well, if I differentiate y implicitly, I end up with dy over dt. And if I use the product rule implicitly, differentiating t times dy over dt, we end up with dy over dt plus t times by d squared y over dt squared. And if I simplify this, we can see that d squared x over dt squared is equal to 2 dy over dt plus t times by d squared x over dt squared. So what we'll do is we will call this 1 and we'll call this 2, we'll call this 3, and we'll call this 4. And what we'll do is we'll substitute in 2, 3 and 4 into 1. So if I take a look at what 1 is, I've got t squared multiplied by dx squared over dt squared, and what that is this result here, and here actually we've got a y, and then we've got minus 2t and then we multiply this by dx over dt, so I multiply by this result here, and then I've got 2x, so I've got 2 times by, well, x is ty, and then I've got 16t squared x, so I've got 16 t squared times by x, which is ty, and this is equal to 4 t cubed sine 2t. So now let's expand out. If we were to expand out, I've got t squared times by t times the second derivative of y, so that's t cubed times by d squared y over dt squared, and then I've got 2 t squared dy over dt, and then I've got minus 2ty, then I've got minus 2 t squared dy over dt, and then I've got 2 ty, and then I've got 16 t cubed y equaling 4t cubed sine 2y. So let's think about what simplifies this, and then we've got this and this, and then if I divide through by the t cubes, what we end up with is d squared y over dt squared plus 16 y equals 4 sine 2y, and that's what we wanted to show. Part B, hence find a general solution for the displacement of P from O at time t minutes. So what we need to do is solve this differential equation. So for part B, first thing we can do is find the auxiliary equation. I've got one second derivative, so my coefficient of m squared is 1. And I've got 1y, rather I've got 16y, so that means my constant term is 16. I've got m squared plus 16 equals 0, m equals plus minus 4i. And therefore, for my homogeneous solution, we'll call it YH, we have a times by the cosine of 4t plus b times by the sine of 4t. Now we need to find our particular integral. So for our particular integral, well, on the right hand side we've got 4 sine 2y. So for our particular integral y pi, let's try lambda times by sine 2t plus mu times by cos 2t. And if I differentiate dy over dt, that's equal to 2 lambda cos 2t minus 2 mu sine 2t. And if we differentiate once again, then we have minus 4 lambda sine 2t minus 4 mu cos 2t. And what we can do is now substitute these back into the differential equation. So we've got our second derivative, and then we add on 16 lots of our function y, this will equal the 4 sine 2y, as we see here. So we've got 12 lambda sine 2t plus 12 mu cos 2t equals 4 sine 2t. And if we compare coefficients, well, looking at the sine 2t's, I've got 12 lambda of them on the left hand side. On the right hand side I've got 4 of them. So lambda is equal to 1/3. And if I take a look at the cos 2t's, I've got 12 mu on the left hand side, 0 on the right hand side. Mu is 0. So for my particular integral, I'm left with 1/3 sine 2t. And what I need to do now is find out my general solution, which is the sum of the homogeneous and the particular integral. So my general solution, I've got my homogeneous a cos 4t plus b sine 4t plus my particular integral, which is 1/3 sine 2t. So here is my general solution.